next talk will be combinatorial algorithms for optimal design problems, and Vivek will give the talk.
Thank you. All right, I'll talk about some optimal design problems. This is in joint work with Mohit and Tao at Georgia Tech and Wejun at Virginia Tech. So let's start with a linear regression setting. Suppose we want to predict some parameter theta star, and we have some experiments, k experiments. If you perform the experiment UI, we observe the dot product of UI and theta star along with some noise. Throughout this talk, I'll assume that this noise is IID Gaussian noise. Now suppose once we have these observations, we do the most likelihood estimate, which is same as the least square error estimate in this case. That turns out to have a nice closed form expression. And if you look at the error vector, because the original noise was Gaussian, the error vector turns out to be a multidimensional Gaussian with mean 0 and covariance matrix, which depends on the set of experiments we have. And just like we have confidence interval in the one-dimensional case, we have the confidence ellipsoid in the larger dimension case, which determines how well our estimate is. All right, so how do we measure the accuracy of our estimate? There could be a lot of different measures. We look at two particular ones. One is we look at the L2 square norm of the error, and we take the expectation. That turns out to be same as the trace of the covariance matrix. And the other measure is if we look at the volume of the confidence ellipsoid, that turns out to be the square root of the determinant of covariance matrix. Now in a traditional setting, our experiments are fixed, but suppose we can choose the experiments we want to run such that these errors are small. So we have a set of n possible experiments, but we have some budget. We can't run all the experiments. We can run only k of them, such that we want to minimize these two measures of error. So if we are minimizing the trace of covariance matrix, that's known as the A-optimal design problem. If we are minimizing the determinant of the covariance matrix, that is known as the D-optimal design problem. So in A-optimal design, we are given n vectors in D dimension and a budget k. We want to pick k of these vectors such that the trace of the covariance matrix is minimized. In D-optimal design, again, we are given n vectors. We want to pick k vectors such that the determinant of the covariance matrix is minimized. For normalization purposes, we have this 1 over d in the exponent. All right, so what do we know about these problems? There are actually a lot of results known about this problem. So first of all, both of them are NP hard. So we look for approximation algorithms. And the general theme of approximation algorithm is this, that if the number of vectors we are picking is sufficiently larger than d, then we can design polynomial time algorithms which always return a solution which has cost within 1 plus epsilon factor of the optimum cost. So we can get 1 plus epsilon factor approximation algorithms. And how do these algorithms work? They start by formulating a convex relaxation, solving the relaxation, and then rounding the solution. Unfortunately, both of these steps, although they are polynomial time, they are computationally expensive because polynomials are large. And most of all, these are actually not the algorithms which are used in practice, though they are very beautiful algorithms, but they are not used in practice. The algorithm which is used in practice is a very simple algorithm called Fedorov exchange method. It's the local search algorithm. So what's a local search algorithm? Let's say we have some n vectors. We want to pick k vectors. We start with an arbitrary set of k vectors. And if we can improve the objective, so for example, if we can decrease the trace of the covariance matrix by switching one vector from the picked vector to one which is not in our set, we make that swap. And we keep doing this till we can actually make a swap to decrease, let's say, the trace if we are working with A design problem, and the determinant if we are working with the D design problem. And when we can't make any such swap, we return the solution, and that is local search algorithm. So this is a fairly easy algorithm. It turns out that it works very well empirically as well. So over the past 30, 40 years, there have been a lot of papers proving experimentally that this works. And that's why it's implemented in several softwares. But even though we knew that this algorithm works very well in practice, there was no theoretical bounds proved for this algorithm. And that was our motivation in this work. For local search for, let's say, A design and D design problem, can we prove worst case theoretical guarantees? There is another algorithm which has pretty much the same story, which is greedy algorithm, where we start with some small solution and we keep adding if our budget is not fulfilled, and the vector we add is the vector which would improve our objective the most. All right. All right. So now what do we prove? We have a lot of different results, but the main idea is that we can get virtually the same kind of guarantees that were already existing due to convex relaxation and rounding. We can get roughly the same kind of guarantees by using local search and greedy algorithms. So what we knew empirically actually works. So what's the result? That if the number of vectors we are picking is sufficiently larger than the dimension, then both local search and greedy solutions are within 1 plus epsilon factor of the optimum. All right. Now, how do we prove our results? We prove by this methodology called dual fitting. Unfortunately, I don't have time to go into the detail, but the basic idea is this. We have a local optimum solution. Let's say we want to show that it is within a 1 plus epsilon factor of the optimum objective. Now, we can't directly compare it. So what we do is we formulate a convex relaxation. Then we formulate its dual. By strong duality, the convex relaxation and its dual have the same objective. And then based on the local optimum solution, we construct a dual solution. And we prove certain lemmas and compare the cost of the local optimum solution with this dual solution. And we show that the gap is at most 1 plus epsilon, which would indirectly prove that the gap between our local optimum with the optimum solution is within 1 plus epsilon factor. Now, as I remarked earlier, that solving convex relaxation is computationally expensive, but our algorithm actually does not solve any relaxation. The formulation of the relaxation is only used for the purpose of proving. The algorithm doesn't even know about convex relaxation. All right, here's the summary. I motivated to D and A design problems where the objective correspond to some measure of error in the linear regression setting. And we want to pick k vectors from a set of possible n vectors such that if we do the linear regression with those set of experiments, our error is small. Now, even though I motivated from linear regression, there are other problems related to this. For example, determinantal point processes or network design problem where we want to maximize the number of spanning tree by selecting only k edges, or we want to minimize the average effective resistance of the graph. Theoretical guarantees were missing, even though we knew empirically that local search and greedy worked. And in this paper, we close this gap and we show that we can get roughly the same kind of guarantees as we know by other algorithms. Thank you.
Does randomization help in this problem?
Random local search?
Well, yeah, just kind of when you swap, pick one at random, or what do you want to pick the best one? You pick any, right?
Right.
Why don't you pick the one that does the largest result?
I think it would help in the running time. Yes, it would help because, yes, it would help if we, especially if we, rather than doing the normal local search, if we have this 1 plus epsilon local search, which is we only swap if the objective improves by within like more than 1 plus delta factor. And in that setting, when we care about the running time, it would help. Right now, we were not really worried about exact running time. First, we wanted to show that local search and greedy works, and then we showed that some variants of the local, like the faster variants also work. And I think, yeah, random or the best one would help. Yes. The running time would be sensitive, but it's not like the guarantees we prove here are not sensitive. It doesn't matter where you start with. Any local optimum would be within 1 plus epsilon. Okay, so not really. I mean, we are working on some problem where we can't pick any k vectors. We can only pick from some method. But this problem by itself, no. So one is, okay, if you like method, you probably like submodular function. So the objective for D design, that is log submodular. So maybe it would work, but again, the thing is, to get a 1 plus epsilon approximation here, we need additive approximation for submodular, which does not exist. So it's not quite the same. So suppose I have a graph, I want to pick k edges such that the resulting subgraph has maximum number of spanning trees.
Yes, I'm trying to understand what is D in that case.
What is, oh, D is the number of of vertices. So we have to have the number of edges we pick is at least, it's n minus 1, not the number of vertices. Number of vertices minus 1. And if we have number of edges we want to pick more than the number of vertices minus 1 over epsilon